Mr. Richmond, and this is your Unit 6.1 lesson summary. Unit 6.1 will be on solving systems of equations, both graphically and algebraically. A system of linear equations is when two or more equations define a relationship. So you'll see throughout the book several different word problems where there's actually two different equations that can define the situation. There might be a restraint on the price that they can spend. At the same time, might be some restraints on the quantities that they need. So you start to look at two different relationships in one situation, which will have two equations. So we're going to need to find a solution to that. We're going to have to find a way to solve that system of equations. The solution to a system of equations is the intersection points of the graphs of the equations in a system. So the first way you'll see to solve these is just by graphing the two equations that represent the situation and finding the point in which they intersect. We can also solve them algebraically though. One of the first methods we'll learn is substitution. It's a method for solving them in which we take one variable and isolate it, so we have an expression for that variable, and then take that expression and substitute it in to the other equation. Then from there we can solve it out because we'll only have one variable in the problem, and we can take that answer and plug it back in. So I'll show that whole process. In addition to that, we're going to start to define our different types of systems. We have consistent systems and inconsistent systems. A consistent system is any system that actually has a solution, whether it's one solution or many. If it has an answer, it's consistent. If it has no answer, we call it inconsistent. It's one solution if the lines have one intersection point. That's why the y-intercept can be the same or different, but the lines must intersect to be a one solution consistent system. To be a many solution consistent system, your y-intercepts would have to be the same and your slopes, because the lines would actually be the exact same line. So you get a many solution situation when the lines are right on top of each other. So the main ways you will be telling is through the process of solving or by looking at the graphs. If the lines intersect, it's consistent, one solution. If the lines are exactly the same, consistent, many solutions. And if the lines are parallel, inconsistent, no solutions. So hopefully that table there, if you want to copy it down, I believe it's also in the book on page 381. You want to make sure that's filled in real well because that'll help with the classifying portion. Okay, let's jump right into some sample problems and let's try solving by graphing. So the first one I gave you is y equals negative 2x plus 4 and 2x minus y equals 16. I'm just going to graph each of these two lines individually onto the same coordinate plane and hopefully find their intersection point. So the first one, y equals negative 2x plus 4, I see I have a slope of negative 2 and a y-intercept of 4. So I'm going to graph that using slope and y-intercept by going up 4 and plotting my y-intercept. And then I'm going to go down 2 over 1, down 2 over 1. And you'll notice here, I've already started to get my line. Okay, I'm on a whiteboard, so again, it's a little tougher to keep this looking nice. But I'm not going to just draw my line like you have in previous sections. Even though I have 2 points, I want to try to extend it out and get as many points as possible. Because I'm going to want to find their exact intersection point, and it'd be best if I wasn't kind of guessing that because my line was drawn straight. My line wasn't drawn straight enough. It's going to be tough to see where they actually intersect. So I suggest extending out your slope to as many of those points as you can. And as you see here, it's really hard for me on a whiteboard to keep this looking nice. So graph paper is a must here for this section. 2x minus y equals 16. Now this is in standard form, so I'm actually going to graph this a different way. I'm going to go for the x-intercept, y-intercept method of graphing. It's a good review for us too. So to get an x-intercept, you make the y be 0, you plug in a 0 for it, and then you solve. 2x equals 16, so x would equal 8, making my y-intercept 8, 0. To find the y-intercept by plugging a 0 for x, solve, divide by a negative. So my y-intercept is negative 16. And I plot that. And actually here, I'm going to have trouble with that, I don't think, for my scale. So 1, 2, 3, 4, 5, 6, 7, 8. So here's 8, and my x-intercept is 8, 0. And I'm actually going to figure out the slope here. If my slope was, my y-intercept was down at negative 16, it'd be going up 16, so rising 16 and running 8, which means ultimately it just has a slope of 2. So since it has a slope of 2, I'm going to do something a little trickier. Something you haven't seen us do here is, since my y-intercept wasn't on my scale for what I wanted, I'm going to graph the line without it. I'm going to figure out the slope by looking at what the rise and run between the intercepts would have been, and go up 2 over 1 and down 2 over 1 and start plotting points. And attempt to find the intersection point. Now, again, if I was using graph paper, this would be much easier to find this intersection point because I'd have my grid. Here, I'm going to have trouble. So 1, 2, 3, 4, 5, I hope, and down to what looks to be 1, 2, 3, 4, 5, 6-ish. So it looks like 5, negative 6 is my correct point, but I'm not on graph paper. I want to whiteboard it, and it's really kind of shifted off. So I want to check if this answer works. Especially with graphing, especially if it's fractional or decimal points, if it's not right on, you want to try to check your guess or what you thought your intersection point was. So let's plug that into the original equation and see what happens. So I need to plug in a negative 6 for y here, a 5 for x, and I need to work that out. Negative 6 equals negative 10 plus 4. And negative 6 equals negative 6, so it did indeed work for the first equation, but in a system it has to work for both, or all. So let's try the other one. 2 times 5 minus a negative 6 should equal 16. Zip zap, 10 plus 6 is 16, and 16 equals 16. It checks for both, so that is indeed the solution. So I'm going to write my answer as a solution. So the solution to this system is 5, negative 6. And it says to classify it. Well, to classify it, I just say what type it is. Is it consistent or inconsistent? Well, we have an actual solution. So since I have a solution, it is a consistent one solution system. Now, as you can see, I ran into some issues there graphing, especially if I didn't have the right tools, if I didn't have my graphing calculator, I didn't have graphing paper, it could be a bit of a pain there. So we do have an algebraic method, which is nice because it's easier for decimal answers, fractional answers, answers that maybe aren't nice and easy to put on a graph. That method is substitution. When we solve by substitution, we're going to try to find what one variable equals, y or x, isolate it, and then plug it back into the equation. So the way you choose that variable is very important. You want to find the one that's going to be the easiest to isolate. And if I look here, x and y are on the same side, so that's going to involve a good amount of work to isolate. If I look here, y or x are both pretty much also already isolated. I just have to get rid of the coefficient 0.1. So for this one, I'm going to solve for y. So you want to be real careful about choosing a variable you're going to solve for and planning the problem out before you attack. Now, I went ahead and put one that had a lot of decimals in it because I wanted to show you a nice little trick here. A lot of us don't like to work with decimals. You'd rather work with whole numbers. That's fine. If you have decimals, just multiply by 10 or 100 to get rid of them. If all your numbers have one decimal place, multiply everything by 10. Now, when I say everything, I mean both sides of the equation. Okay? By doing that, you'll get more reasonable numbers. So I'm going to multiply both these equations by 10, both sides. So 10, 10, and 10. 0.4 times 10 is 4x, 0.3 times 10 is 3y, and 1 times 10 is 10. On the bottom, 0.1 times 10 is 1, so 1y, equals 0.2 times 10 is 2x. And just like that now, the decimals are gone, I'm working with more reasonable numbers, and my variable is now isolated, y. So y is equal to 2x, which means anywhere in this system, y should always be equal to 2x. So that means I can take what that y is and substitute it into the other equation and rewrite it. So that's what I'll do now. 4x plus 3, and you'll notice I always use parentheses when I plug it in. If you do not use parentheses when you plug it in, there's a possibility for mistakes. So I'm going to plug in 2x for the y, and finish writing the equation. So you can see the only difference between the top equation now is I've substituted the y, replaced it with what y equals, which is 2x. Now I solve that linear equation. 4x plus 6x equals 10. So 10x equals 10. Divide both sides by 10 and x equals 1. So I'm almost done. I've now solved one variable in the system, and I can take that now and plug it back into either of the original equations or either of the simplified equations. Y equals 2x looks like the easiest one to me to substitute in for, so that's what I'm going to do. Y equals 2 times 1, so y equals 2. So my answer to my system should be, and I'm going to write it now. You notice I got an algebraic answer, an answer for x, an answer for y, but a solution is always an actual coordinate, an intersection point, so I need to write it that way. 1, comma, 2 should be the solution to the equation. Okay, if I plug it back in, 2 times 1 is 2, so that works, and 4 plus 6 is 10, so it works in both equations. If they ask me to classify it, I can classify it as well, but again, I got an answer. As soon as I get a normal coordinate answer, I know it's consistent with one solution. Now, I did want to do one more substitution one with you, so you can see maybe one that isn't going to be always be consistent, one solution. So let's try solving this by substitution. Now, again, I need to try to solve for a variable. If I look at the top, x and y are not isolated, but down here y is. So this would be the easier one to use for your substitution. And if y or x wasn't alone, I'd get it alone first. Same step, take it, plug it into the same variable for the equation, and make sure to use those parentheses. And here, if you did not use the parentheses, it would not end well. So 6x plus 3 times parentheses negative 2x plus 1 equals 5. I've just replaced the y with what y was equal to. Now I have to solve that linear equation. I'm distributing 3 times negative 2x is negative 6x. 3 times 1 is 3. Now whenever I'm solving an equation and the variables are on the same side, I want to combine like terms. 6x minus 6x is 0x. And 0x I don't need to write, so I end up with just 3 equals 5. This will be a sign that you have a system that doesn't have a normal answer. I ended up with something like 3 does not equal 5. If the last statement you're reading after everything's been simplified is a false statement, then there is no solution to that. So this has no solutions, and because it has no solutions, this system should be inconsistent. The only other thing that could happen, and again this is not part of this problem, is you end up with a true statement. If something like this happens and your statement's true, then it has many solutions. Because it doesn't come up with one answer, it works all the time, and that is a consistent system. So you can also see this happen while trying to solve these systems with substitution. So hopefully this helps. Thank you. This is the start of the systems chapter. It is a difficult chapter, but if you get the first few sessions, it should go pretty smooth. Thank you and good luck.